Okay, then the idea for this second notebook is to use some of this same kind of data visualization that we just learned how to do in the first exercise to look at changes. So far we were just looking at one rainfall data or the average of 1 year or a single Landsat scene, but a lot of the value of the data that's on Earth Engine is that it covers a long time period. So you can look at changes through time. Changes between the summer and the winter, changes between the 1980s and the 2000s, these kinds of things. And there's a lot of different kind of contexts you might want to look at changes detection, right? You might want to look at land cover changes as there's been more urbanization or more agriculture, or for example, glaciers that are retreating or glacial lakes that are growing. I know that's quite a big topic here in Nepal. So we're going to look at differences between some distinct time points. We're going to look at differences between averages between different years, so the average of the year 2000 versus the average of year 2010. And then we'll also look at trends. So how can we calculate a trend through time and also visualize that? That's the idea for this second notebook. So we, just like before, we can open up our project and check that it's working by running our same little piece of code here. And then the next thing I want to do, or the first thing I want to do, is I want to focus on some glacier lakes. So I'm sure you guys are quite aware that the glacier lake floods are a big problem in many parts of Nepal. So I've found one glacial lake that has been growing over the last years. And I found the point for it. So this is just like before, we're defining a geometry point, so a point location of interest. And I'm using that lake center point to filter my Landsat 9 collection. And again, I'm using my same scale factors. This is exactly the same code we just used in the previous notebook. Again, I'm choosing the first image, applying some scale factors, and making my true color visualization, just like we did with the image over Kathmandu. And if we look at this, we should, in a second here, have a look at one high elevation area. My point here is focused on one lake on the end of a glacier. If you zoom around a little, you can see that there's several different glaciers here, and many of them also have lakes at the end of them. So I'm focused just on this one here as a first test, but these lakes, I think, are also changing, and these glaciers are also retreating. Now, we could load a different image, so an image from a much earlier time period, and just try to flip back and forth and compare them to one another, or print out two maps and try to find the differences. But since we're working directly in Earth Engine, we can actually make a little visualization that shows both at the same time. So we can use like a time slider to flip between these two images and look quickly at changes. To do that, we have to find an image from an earlier time period. Landsat 9 only goes until 2021, so it's quite recent data. If we want to look at much older data sets, we have to use a different Landsat collection. So, for example, here, we're looking at Landsat 5. So Landsat 5 started collecting data in the 80s, and it stopped collecting in about 2012. So if we load in our Landsat 5 data and do the same filtering, we can apply scale factors. If we look at this data here, the scale factors are a little bit different than they were for Landsat 8. This is a much older sensor here. But we can see that we have data from Landsat 8 from 1984 until 2012. So if we want to look at historical imagery, this is a really, really good resource. We have quite similar bands. So we have these band 1, 2, 3, 4, 5, 6, 7. They're not exactly the same as they are for Landsat 7, 8, and 9. So some of the bands have changed between the Landsat sensors. But for doing a true color image, we can use the same kind of scale factor, and we can choose one single image, just like before. In this case, I'm choosing one image that starts in June, so I want a summer image. So my first image here should be something during the summer of 1998. And my bands for true color are a little bit different. It's 3-2-1 instead of 4-3-2. Landsat 7, 8, and 9 have an extra atmospheric band that they didn't have on Landsat 5. So the red, green, and blue channels are 3-2-1 for Landsat 5. And if we look at this over the exact same lake and the same area, it looks a little bit different, right? But it's kind of hard to go back and forth and try to find the exact difference by going back and forth between these images, right? So thankfully, since this GEE map module is quite convenient and well developed, there's a function to make a split screen map. So we can scroll back and forth and really see the differences. And all we have to do for that is we use the same visualization parameters that we had before, and we load in with GEE map our left data set, so our earlier data set. And on the right side, we load in our 2025 data, our more recent data. And we keep the same center point, and we use, instead of a simple map, a split map. So this will take however we visualize these two things and make a split map, and we can look at these two things together. And hopefully this runs pretty quick, and now we can go back and forth and see that in the 80s, that lake was a lot smaller than it is now, right? So the left-hand side is 1998, I guess, and the right-hand side is 2025, something like that. And we can see that maybe these two lakes here on the right aren't moving so much, but this one is growing quite a lot, right? And it's also, the glacier is changing and thinning, and we can quickly see these things. We can also zoom around and look at some of these other lakes that were maybe interesting and see how they've changed, if this loads for a second here. And we can see that this lake has also grown quite a lot, right? This one has not grown quite so much, but this one, the glacier sort of ended here. And now if we go to the more recent data, it's come way back here, and this lake has gotten quite a lot bigger. So this kind of thing can be really helpful for exploring analysis, right? If you have a bunch of data from 1998 and a bunch of data from 2025, and you just scan around and say, okay, which lake is maybe worth spending more time investigating? Where should I do more detailed analysis? This is what, like four lines of code we put in here, right, to make this map, and then we can do this exploratory analysis. It's quite quick and easy to do this. All right, so the other thing we do, we did a quick intro to this when we did the average rainfall, but the more in-depth introduction to what kind of math we can do with Earth Engine is that Earth Engine works with these things called reducers. And what a reducer is, it's just a general term for any operation that reduces the size of your data. So if you have 5 years of data, you want to reduce it into one image. If you have 5 years that cover the entire globe and you want to turn it into one value for each point on the globe, you're reducing your data set. And the way you do this, you can do a sum, you can do a standard deviation, you can do an average, correlation, all sorts of things. And there are tons and tons of different reducers that Earth Engine has. We're definitely not going to cover all of them. Some of the most common ones you might think of as sort of minimum and maximum, or doing a histogram, or a linear regression we'll spend more time on. There's also mean and max and these kinds of things. Depending on what you actually want to do for your analysis, there's probably a reducer to help you compress your data set into the form that you want. So to do a quick long-term average map, the example that I chose is to use NDVI data. so vegetation greenness data. NDVI is basically a proxy for how much chlorophyll there is in plants, so how healthy and productive they are. If they're very high NDVI, they're quite jungle-like, they're quite productive and happy. If they're low NDVI, it's something more like a desert shrub or someplace where there was a big fire, things like this. So if we look at trends through time, we can see are places getting greener or are they getting less green? Has there been more droughts or has there been more rain? These kind of things. The data I'm going to use is MODIS data. So if I click this, we can have a quick look at the data set. This is the same satellite which is measuring the burned area from the exercise or the example I did earlier in the morning. But you can also get all sorts of different data from it. You can get snow cover, you can get vegetation, you can get surface temperature. MODIS carries a very wide range of instruments that can be used for all sorts of different purposes. Based on that MODIS data, we have these vegetation indices at a 16-day resolution, so once every 2 weeks, basically, globally at 500 meters spatial resolution. All of that info is then in the dataset description. We have the pixel size, these kind of things here. And if we look at our data, the vegetation indices that they store are NDVI, which is the normalized difference vegetation index, or the EVI, the enhanced vegetation index. They're both quite similar. NDVI is the more commonly used one. EVI works a little bit better in places like rainforests, but they're both doing something quite similar. And they have this scale factor in them, again, because of this data storage issue. So it's much easier to store these integer numbers than floating point numbers or numbers with decimals. So if we want to work with this data, we can load in our MODIS image collection and select the NDVI data. So we only want to work with the NDVI data. And then we have to rescale each image. So this little function is just doing that rescaling for us. It's the same as this apply scale factors definition that we use for Landsat. It's just instead of applying the scale factors to one image that has many bands, we're applying the scale factors to many images that have one band that is the same. So the syntax is just a little bit different, but it's just adding some scale value and multiplying by some scale value, which I took from the documentation. If I run this, I can look at what we get out of it. If I take my first MODIS image and I do get info, it's not going to give me the whole global data set. It's not going to try to download everything. What it is going to give me is some metadata. So this will tell me what bands I have available, what their minimum and maximum is, what the spatial dimension of my data set is, and some geographic information about how to plot it and how to project it. It will also tell me the date. So my first MODIS image that I have here is the year 2000, February 18th. If I want to look at something simple like a long-term mean, I can take my data set from 25 years of MODIS data, use a reducer, and then I choose which reducer I want to use. This could equally be a maximum, or it could be a sum, or it could be a min. There are, if I could be a minimum, there are a lot of different reducers available for any kind of math that you might want to do. And again, we're just making the same kind of map, centered, same place, Kathmandu, with some color scale. This time my minimum is going from 0, and my maximum is going to 0.75. So that would be like a no vegetation area or an area that has lots of water to a very, very green area. And this is, again, every 2 weeks, 25 years of data, and it should come up pretty quickly over the whole Himalaya. So this is then the orange color is this first color, and the green stuff is the high vegetation. So the plateau has much lower vegetation, but you can see that some of these valleys that are going up are still quite green until they hit a certain elevation. We can similarly use a standard deviation reducer. The only line I'm changing here is switching out my mean reducer for standard deviation, and that will tell me something about my vegetation variability. So is it low variability, also up here in the plateau, but also in the sort of parts of the Ganges that are always green and that are always irrigated? They have low variability, even though they're quite green, versus the places that have high variability are exactly these valleys that are sometimes covered in snow and have really seasonal vegetation. We can also, since we have these filters, we can do these mean operations over only subsets of our data, right? Just like we chose a Landsat scene from the 1990s and a Landsat scene from the 2020s with a date filter, we can put these two commands together. We can take all of our vegetation data, which is stored here in Modus. We can filter to only use 2001 to 2003 and calculate the mean. We can do the same thing, storing it as Modus mean number 2 for 2010 to 2012. And if we use this same split screen, like we did to look at the glacier lake, we can look at the difference between the average vegetation in the early 2000s versus the late 2000s. And if I remember correctly from when I looked at this, there are definitely differences here, but they're not so huge. If you scroll around, you might find some areas that have changed, but the changes aren't so prominent. Yeah, I don't see many differences here. The averages between these two time periods are quite similar, but they're not exactly the same. So one other way we could visualize this is we could subtract the two, right? We want to know what the difference in the average NDVI is in our late period versus our early period. And to do that operation in Earth Engine, we only have to subtract them. We can take our Modus mean, which is our 2010 mean, and subtract our 2001 mean. And that will give us a Modus difference. If I scale my color from negative 25 to positive 25, I can quickly look at whether vegetation has gotten more green or less green, and where. And doing that whole operation is, again, running quite quickly and only taking a couple lines of code. And what I see here is that, let's see if it loads. As soon as you start doing more and more operations that take more math, it starts going a little bit slower. But it should, for everyone, show up as a mostly blue image. So mostly vegetation has been getting greener. As there's more carbon dioxide in the atmosphere and some of the monsoon strength has increased, plants are generally getting greener, especially in some of those high elevation valleys where it used to be too cold and now it is warm enough for these plants to grow a little bit better. The NDVI has been increasing. So maybe let's take maybe a 10-minute break here, and then we'll go through this last piece of this note. So the next little piece I have up here is exactly the same as what we just did, looking at differences in NDVI through time. Instead, I'm looking at differences in snow cover. So I'm using the same dates, or slightly different dates, 2001 November until 2002 March. So the winter season for 2001 to 2002, and again, 2010, 2011. This is again based on Modus data. If I open up this data set link, we can see that this is daily global snow cover at 500-meter resolution. So we have every day from November to March, the snow-covered area for each point on the globe. And this band, this is what we're interested in, this NDSI snow cover, which goes from 0 to 100. So it's a percentage snow cover for each 500-meter area. So what we're doing here then is every time I leave this there, is we're loading in our snow cover data set, selecting this snow cover, fractional snow cover variable. I'm getting the average for this winter season and the average for the next winter season. I've added one more little piece in there, which is masking the data. So I'm only interested in places that had some snow. If you look down in the Ganges, there's never any snow, so the difference between these 2 years is not particularly interesting. So I can check my average data, make sure that it's above 0.1%. So if my snow cover average is 0, I'm going to ignore those areas. And I do the same thing for my late period. Now I'm doing the same tile layer, so this split screen thing that we did before, and in this we should be able to see some more differences than we saw with the vegetation cover. The difference in the snow cover from year to year will be a little bit larger than the difference in the vegetation cover. So if I look here, I can see that the snow cover was higher in my early period, so 2001, and 2010, it's quite a lot less, right? If I'm looking up in here, this darker blue means there was more snow cover, and the lighter blue means that there was relatively less. So this is one quick way to check, was this a quite snowy year or a less snowy year? And again, we can load this over our whole region quite quickly. We can, in the same way, also do this difference, exactly what we did with the vegetation data, and this should quickly show us that we have less snow cover in this area that we were highlighting, right? This is all red, so it's 10 or 15% less snow cover in the 2010 year than in that 2001 year. But it's not everywhere. This was a much snowier year over here, for example. All right, so the last part of this exercise that I want to go into is trends. So far we looked at single images, and then we looked at differences between averages of years, but often what you want to know is how fast are things changing? What is the trend in temperature, or the trend in rainfall, or the trend in vegetation cover? One data set that's commonly used for looking at temperature trends, for example, is this ERA5 data. And this is a global climate model that is also integrating weather station data and satellite data from around the world. So it's a very high quality product, and it's running from 1979 until 2020. So it's still running up until today, but they only have these monthly aggregates on the older period of data. But 1979 until 2020 is still quite a long period of time, long enough that if we look at temperature trends, we should see some signal. This is monthly data, so it's these monthly aggregates. If we look at the bands, we can see that we have some useful ones. For example, our average air temperature or our total precipitation. We also have different things like surface pressure or wind components. There are a lot of different variables available from ERA5. It's a climate model that covers the whole globe at 30-kilometer resolution. What we're going to look at today is this air temperature and precipitation, and just try to make some quick maps and see if we can see some climate change trends. So to do this, we're going to load in our monthly data here. We can again check the size, just like we did before, and it should tell us that we have quite a lot of data. We have about 500 months of data, So that's quite a nice detailed data set to do some trends on. And the next block here has a couple pieces of code, two different definitions. One is selecting my total precipitation band and converting it from millimeters or from meters to millimeters. Basically, if you try to do a trend and the values are all too small, you're going to get a trend that's very close to zero, and it might just give you back a zero value. So we're just multiplying this to make the numbers a little bit bigger, going from meters to millimeters, and then we're going to get our trend results to be a little bit more accurate. To actually run the trend, we can give in our data collection and choose some variable. In this case, we want total precipitation. And when we want to do this kind of regression through time, we have to tell Earth Engine what the time actually is. So we need a band or a set of dates, and we need a set of values. So this is what this little function is doing. It's getting the date from each image, checking how far away it is from the year 1900, so we can make sure that we know what the units of our trend are. Is it millimeters per day, millimeters per month, millimeters per year? In this way, we can make our date registered to one date, and we know what our trend units are. And it's making a constant band with that date. So now we know what the units are for our time array, and we know what the units are for our millimeters of precipitation. And we use, again, a reducer. And in this case, it's a linear fit. So this will perform a linear regression at every single pixel over the globe and give us that slope result back. So first, I'm converting my monthly data to millimeters, and then I'm running my time regression on this millimeter precipitation data, and I turned off the TV, sorry. One second. So, what we're taking out of here is this scale, and this is the trend coefficient. This is the slope of that regression. And it's called scale because that's what Earth Engine decided to name the scale factor for this regression. If you run this, it's not actually going to put anything out. It's just setting up this calculation. Until we make a map or export the data or try to check a value, it's just preparing. It hasn't actually run anything. So it just runs very quickly. It's setting up this calculation. And then as soon as we want to make a map, in this case, I'm running some longer color bar here, which I've told you a little bit more detail, that blue will be more rainfall and red is less rainfall. And once I try to make this map, it will actually do the calculation for me, and it should, hopefully fairly quickly, give me a precipitation trend. And this shows me that, according to the ERA5 data, from the 1970s till about 2020, there's been more precipitation throughout most of Nepal, and less in some parts of the Indus and over here in the eastern chunk of Tibet. And just like we did before, we can also check those trend values, right? And we can see that, for example, in this place I chose, this is a scale of 2.33 millimeters per year. So there's been an increase of 2 millimeters of rainfall over that area per year in the last decades. So this was quite quick, right? That ran super fast to use this 500 months of data and perform a trend analysis, and we can quickly look at a map. We can do the same thing with our MODIS data, for example. This is setting up the same kind of regression. I'm getting in my vegetation data again, selecting NDVI, rescaling it, and again, I'm now giving it a scale factor of 100, so I'm making it a little bigger so the regression has something to work with. And I use this same time regression function that we just used for the precipitation data to look at a trend in NDVI. And if we make a map of this, It will go a little bit slower since we are now making a map of 500 meter pixels instead of a map of 30 kilometer pixels. It has to work with much more data, but actually it came fairly quickly. And we can see that as before, the blue areas are places where there is a positive NDVI trend, so they're getting greener. And the red areas, mostly little places where potentially the river has shifted its course a bit over the last 20 years, those are areas that are getting less green or more water covered, for example. So this is something that you can also zoom around in. It's not limited to where you first center your map. As you move the map, it will try to calculate each of these tiles so you can look at different areas and you can check out if some places have had higher trends and less trends. Zoom in, zoom out, and it will calculate for whatever area you happen to be looking at.